Hi, welcome to this new lecture of Math-S401 dynamic optimization. Today we're going to look at value function iteration. So in the previous lectures we have seen all the mathematical concepts and tools surrounding the Bellman equation and the Bellman fixed point and so on. Today we're going to see how to use a computer in order to apply these concepts. And the first part we're going to work with is called value function iteration. So we call, if we have a Bellman operator, can be written like this: TV of the state x is the maximum over actions in some correspondence g of x of the instantaneous utility function of xa plus beta v and then r xa. Okay, so this is the Bellman operator. And if you want to solve the infinite horizon dynamic optimization problem, then basically we have to find the fixed point of this operator. Okay, but because this is a contraction mapping, what we can do is we can start with some function v0 of x. Okay, then plug this in here, and then we apply the Bellman operator tv0. Okay, so which is going to be equal to the maximum of a in g of x of f xa plus bv rxa of v0. Okay, so for every x we solve this problem, we get a new function which is going to be t of v0, and we can call this the function v1, okay, which will be a function of x. Then what we can do is we can plug this back in to our Bellman operator. Then we get a function tv1 of x, and we can call this v2 of x. Okay, so if we do this over and over again, plugging in our current function into the maximization problem, we get a new function and so on and so on. So we get a sequence of functions v0, v1, v2, v3 and so on. Okay, and you know, because this is a contraction mapping, this will converge to our fixed point v star, which is the function that we're interested in, because it will solve our infinite horizon dynamic optimization problem. Okay, so the problem is now how can we compute this v star? Well, in principle it's very easy. We start with any function that we can think of, we plug it in here, we compute a new function, we take this new function, plug it in here, we compute a new function, and so on and so on. Okay, so this procedure of starting with some function, generating new functions by using the Bellman operator, this is called value function iteration, right? Because you iterate the value function over and over again. So mathematically this is all very nice and easy. Of course you would like to implement this on a computer. Okay, and if you want to implement this on a computer, there are a few things that you have to take into account, and the most important thing is that computers don't take as inputs continuous functions, right? Because computers are finite, you can only store finitely many data in a computer. You somehow need to transform this into a finite setting. Okay, so the first thing that you probably need to do is to transform our infinite horizon dynamic optimization problem, which we treated as being continuous, and for example the set x of all states was infinitely big, right? Could be a subset of rk. So now we have to make it discrete, which means that we have to somehow discretize all these sets. Okay, so this will be the first step that you need to do. You need to discretize everything. Okay, so in particular, what we need to do is we need to substitute our infinite set x by a finite set of possible x's. Okay, and let me go big N. Let me call this the size of the grid of the set x. Okay, so here n. So in some way we make a grid, finite grid of possible states. Okay, You have to do the same with the set A. Okay, you have to say there's a state A1, there's a state an action A1, an action A2, and so on. Okay, so maybe there's m actions that we can take. Of course, if we have a finite grid of states, a finite grid of actions, then all these functions f now takes a state here and an action here and produces a number r. Our correspondence g takes a state here and produces a subset of this set A of actions. Okay, so basically we have to transform everything to the finite setting. And then our law of motion, we take a state in here, we take an action in here, and we produce a state in this finite set. Okay, so we have to make everything adhere to this finite setting. Okay, so you can say, okay, but we analyzed this infinite setting and we have shown that indeed, okay, this converges, but we assumed everything to be continuous and infinitely big and so on. Well, you can show that if you make everything finite, right, so if you only consider a finite number of states and a finite number of actions, then all these results also hold. And in fact, it's even easier because if you only have a finitely many x's and finitely many a's, then this function is bounded anyway. Okay, so we don't need all these boundedness conditions on the growth rate of some phi function, right? Remember, we take continuous, and we don't need to bound this f from above by some function phi. Okay, so we don't need all these additional conditions. Actually, if you only have finitely many states, life gets a lot easier from a mathematical point of view. Okay, so this is the first thing that we need to do. We have to make it finite. Okay. Then what we need to do is somehow we have to implement this maximization problem into a computer. Okay, so in order to do this, we have to store the set of states x into some data structure. We have to store this set of actions into some data structure. Okay, and maybe the easiest way to do this is the following. So x, we can put this into some vector, a big vector, right? Let me write it like this. So with values x1, x2, and so on until xn. Okay, so this is we're going to store this in the computer as an n-dimensional vector of size n. Okay, and the ith element, which I will write by I, okay, the ith element of this vector is going to give you the value, the ith value of the state. Okay, so value of state I. Okay, so that's the first thing. Then we can do the same thing with our A. This is A1 until AM. Okay, so here AI, the ith element of this vector will give you the action AI. Okay, then we also need somehow to store the value function. Okay, because at every time we're going to compute this one, and we have to compute this on these finitely many states. Okay, so a value function, you can write it as a big vector v, which is going to have v1 until vn elements, so it's n-dimensional. And the idea here is that v at position I gives you the value function of the state xi. Okay, so vi, which is here the element vi, we're going to define it as being the value of a function v at xi. Okay, and here xi is the ith element of x. Okay, so that's good. A final ingredient that we need is we have to solve this maximization problem. And at some point we also want to store the optimal solution of this maximization problem. Okay, so in principle, once we get to the fixed point, we want to know the policy function that corresponds to this fixed point. So we want to also not only know the value function, but we also want to know what action we should take at each state. Okay, so we're going to store this solution of this optimization problem. Okay, so what do we have here? Here we have a state x. You want to solve it, and this gives us an action A. So we're going to, so previously we called this a correspondence gamma x, which tells you what action to take if a state is x. So we're going to store the solution of this problem into a vector gamma of numbers. Equal gamma 1, gamma 2. So we will need to have a gamma for every x, right? So n of them. And the idea here is that these will be an element of 1 up to n. Okay, so what's the idea here? The idea is that if gamma I is equal to, let's say, k, well, then gamma, if state is xi, will tell you to take action ak. Okay, so it captures the index of the action that's optimal for the position of the state. Okay, so this is how we're going to do it. For example, if we have two states 1 and 2, then gamma is equal to, for example, 3, 7, and says that at state 1 the best thing to do is to take action A3, the third value of the action. At state 2 the best thing to do is to take the 7th element of the action. Okay, so this is basically how we're going to store everything. Okay, and to make my life easier, I'm going to equate the actions to the states, and I'm going to look at the problem. Maybe I should have said this before, but I'm going to look at the problem that we have seen previously, basically where you where the law of motion is the identity function, and what you do is you pick the state tomorrow immediately. Okay, so we're going to take an action A in gamma of x to maximize fx a plus beta va. Okay, so we don't need to distinguish between x and a, and we don't need to make the law of motion r, because here r is the identity. And in many cases we can reformulate the problem such a way. Okay, you can do it also more elaborately, but here I'm going to look at this problem. Okay, so we're going to have to solve this problem using a computer. So here we already have our data structure to save all the states, data structure to save the values, the value function at some iteration, and then a data structure to capture the policy function. Okay, so first thing, so this is a maximization problem. Okay, so for every x and a possible states and possible actions, first thing that we need to do is we're going to have to evaluate this value here. Okay, next step, we're going to have to take the maximum of all feasible actions. Okay, and then next thing we have to do this for every x. Okay, once we have done this for every x, we get a new value function, and then we have to iterate this over and over again. Okay, so let me first start by the first problem. Okay, so first let me, for a given x and a, let me try to, and a given function v, right, which will here be captured by a vector, let me try to compute this value here. Okay, so this is something that we have to solve. Right, so this is going to be a function. I'm going to use some kind of pseudocode here, right? So in order to get the ID straight before I start programming. So let me call this value function, right? This is it's going to take in state x, and state x I can just use the index here. Okay, so let me call this x index. Okay, and this is going to be a number between 1 and n. Okay, then I need to have a value of a. I'm going to call this a index. Okay, there's also a number between 1 and n. Then I'm gonna have to get the value of x and a, right? So I have to somehow give it this big vector here, this vector x, and I'm gonna have to use v, right? So I'm also gonna have to use this value here, right? So these are the inputs of my function. So if I have the x index, right, then my x is equal to x at x index, okay. My a is going to be also my x, a is equal to x here, right, at a index, and then somehow I have to compute this, but this is not so difficult, right? So for, first of all, I have to make sure that a is in it's not gamma but g of x, right? So if a is not in g of x, right, and then I have to, this depends on g of x, right, how it looks like, so I have to write something else here probably. Then if a is not feasible, well, what I can do, actually I cannot compute this, right, because there's no value here. But one thing, because I'm maximizing here, what I can do is I can give it a very, very low value, right, such that the maximum will never be reached at this value. So basically saying that this is not feasible is just giving it a very low value, okay. So here I'm going to return minus infinity. So minus infinity doesn't exist on the computer, but you, in several software packages, you can use it. So this is what I'm going to do here. It's just a very, very big negative number, okay. So if it is feasible, so else, then I'm going to return fxa plus beta times v, right, and here v at a, right, so this is going to be a index, right, so this is which element of v? Well, it's the one for the next state, so it's a index, okay. And I'm ending the if, and I'm ending the function, okay. So this is my function here. This is a kind of function that I can use to compute this thing here, okay. Now, so I can evaluate this for every a. The next thing would be for a given x to compute a maximum here, okay. So this is new function. Maybe I can call it compute the maximum, okay. So what do I need? Well, I will need to have a state, right? So x index, and then I probably also need x, and I probably also need v, okay? Because I'm going to have to pass it this function here. So how can I compute a maximum? Well, I can make a variable, let's call it solution, right? And I can put it at minus infinity to start, and I can I probably also want to store this thing here, the optimal value, okay. I can call this optimal index, and I can set it to something that's just an integer, right, because it's going to store some integer. And then what I can do, well, naively, what you could do is you can iterate it over all possible a indexes, each time compute this one, and if I get a higher value, then I'm going to update solution and I'm going to update optimal index, okay. So that's a possibility, right? So for I equal to 1 up to n, because there are n values of a, what I can do is I can compute value. This is going to be this function here, value f of what, of this at this point x index. My a index is going to be I, and then I'm going to have to give it a value x, and I'm going to have to give it a value v, okay. And then if value is bigger than solution, right, so I have found a value that's better than the solution I have until now, I'm going to put solution equal to value and also going to put opt index equal to I here. I'm going to end this and this, and then I'm going to return solution, and I'm going to also return optimal index. Okay, and this is going to end my function. So now if I run this function for a given x index, I'm going to solve this maximization problem for this x here. Okay. So the thing is, I have to do this for every x, right? Because I want to have my TV of x, which is the next iterate. Okay. So I can do this using a new function. Maybe I can call this what I've called it, value function compute max. Maybe I can call this new value function. Okay, so now I need the set of states, and I will probably also need a vector v of the current value function. And what I need to do is, well, basically I need to iterate this over all possible values of x. Okay, so I will need to store the new value function into something, right? So this TV is going to be just a vector of size n. Right, and I'm also going to get the solution is also going to be a vector of size n. Okay, and then I'm going for let me call it I equals from 1 to n dvi, and then gamma I is going to be equal to this function here, compute max, of which, well, the index for the state, my vector of states, and the value function. Okay, this is going to end, and I'm going to return this entire vector here, and then my gamma here. So this is going to be my third function. Okay, so far so good. So now finally I'm almost done. I need one more function. Basically I have to iterate this over and over and over and over and over again until I get a fixed point. Okay, so how will I know that I'm at the fixed point? Well, in principle you never will reach the fixed point, right? You will get closer and closer and closer to the fixed point, but you will never get there in the end, probably. So what are we going to do? We're going to iterate this over and over again, and we're going to measure the distance from the next iteration to the previous one. And if this distance is smaller than some very, very small number, then we're going to stop the algorithm. Okay. So let me get my function. So let me call this value function iteration. So what do I need as input? Well, basically I only need my states here, right? Then I'm going to have to make a vector of values, right? I'm going to have to loop over each time computing a new vector, so let me call this a vector TV. Okay, and then I'm going to have to get my solution vector is also a vector of size n. Okay, then let me call something to capture or to compute the distance between this one and this one over each iteration, and let me just put it at some big number at the moment. I don't know, let's say 10, right? As long as it's big enough. And I'm going to introduce some very small number. Let me call this epsilon. It's, for example, 10 to the minus 6 or something, right? So it's a very small number. So what I'm going to do at each iteration, I'm going to compute the distance between this and this vector. Okay, and as soon as the distance is below this epsilon, I'm going to stop the algorithm and just give the solution here. Okay, so this is going to be a while loop, right? I'm going to iterate until some condition is satisfied, well, until as soon as distance is below epsilon, I'm going to stop. Okay, so while distance is still bigger than epsilon, I'm going to set TV and gamma to be equal to what? Well, here, new value function of x and v. Okay, then what I'm going to do, I'm going to compute distance is going to be equal to the, what I can do is I can take the infinity norm of TV and V, right? So this is the maximum of the difference between these two vectors. Okay, the maximum of the absolute value of the distance between these two vectors. And then what I'm going to have to do is, if this distance is still bigger than epsilon, I'm going to have to iterate this, but now TV will be here and the new TV will be here, right? So I'm gonna have to set V equal to TV in order to get the new loop started. Okay, so this updates the value of V. So I'm going to end this, and then once I exit the loop, what I'm going to do is I'm going to return TV, and I'm going to return the last value of gamma here. Okay, and I'm going to end this function. Okay, so this is going to be my value function iteration. Okay, so here I split it up, and in principle you can put everything in one big function, okay, which is also reasonably valid, but here I try to split it up into a function that computes for a given state and a given action the function you want to optimize. Then for a given state, this is going to give you the maximum value, right? Then this is going to compute a new value function, right, over all states. And then this one is going to iterate the loop over and over again until you hit the fixed point. Okay. So in order to implement this on the computer, I'm going to focus on one particular problem, right? I'm not going to look at the general function f and so on. No, I'm going to look at a growth model. Okay, that's the name. So in principle, I'm going to look at consumption capital stock trade-off model. So I'm going to maximize C in 0. Now I'm going to have to use a production function. So I'm going to use a law of motion where kt plus 1 is equal to kt, let's say, to the power alpha. I'm going to give a value of alpha in a minute. And then there's some 1 minus delta times kt, right? So a fraction 1 minus delta of the capital stock today gets into the capital stock of tomorrow. And then using the capital stock today, I'm going to be able to produce some output. And then of course I'm going to consume something. Okay. So I'm using CT. CT is going to be between 0 and kt alpha plus 1 minus delta kt. Okay. And then as a utility function, I'm going to use a CES utility function. So this is CT 1 minus sigma minus 1 divided by 1 minus sigma. Okay, so this is a standard concave utility function plus beta and then V, and this is going to be kt plus 1. Okay, so this is my Bellman equation given this law of motion, right? So instead of writing kt plus 1, I could have just also substituted this in here. So the first thing, I'm going to try to get rid of the CT variable here, right? So I'm going to maximize kt plus 1, which is in 0, kt alpha plus 1 minus delta kt, right? So this is going to be my g of kt, okay, of the instantaneous utility function. So if I substitute ct, plug it in here, then I get kt to the power alpha, there's a t at the bottom, plus 1 minus delta kt minus kt plus 1, and then to the power 1 minus sigma minus 1 divided by 1 minus sigma, and then plus beta v kt plus 1. Okay, so this is my Bellman equation, and this is going to give me tv of kt. Okay, so this is a particular instance of a growth model, so I need some parameter values. So let me check which ones I'm going to use, so you can implement it yourself at home. So I'm going to use sigma equal to 1.5. I'm going to use beta to be equal to 0.95. I'm going to use alpha equal to 0.3, and I'm going to use delta to be equal to 0.1, which is the depreciation rate of capital. Okay, so in order to get this model running, what I need to do is I need to write some functions, first to compute this one here. Next, I need a function to compute the maximum for a given kt. I need to compute the optimal kt plus 1. I have to do this for every kt, and then I have to iterate again and again. Okay, so I'm going to use this in Julia, but you can also do this in other programming languages. It's very similar. So let's start programming. So this is Julia, in particular Julia 1.5.3, but all the coding that I'm doing here should also work for earlier versions or later versions. So far what I've done is I've just inputted these parameter values for alpha, beta, sigma, beta, alpha, and delta. So what do we also need? Well, we need a vector to save all the states. So normally I call this the vector x, but for this model let me call it the vector k of capital stocks. So I'm going to use a vector of equally spaced values. So for this we can use the command range. So I need a starting value, let's put it equal to 0, an end value, put it equal to 5, and then a length of the vector. So let's take 100 for now. So we can increase this value later on. So I'm going to change this to a low value, which is strictly positive, because if I start with a capital stock of 0, then next period I will again have a capital stock of 0, and from then onwards every time I will have a capital stock of 0, right? So this is not a very interesting value, so I will start at least some strictly positive value for the capital stock. Okay, so let me first read in all these values. So here I have just a vector of length 100 with equally spaced values. Okay, so now let's start the real coding. So first I need a function, let me call this objective value, okay, which is going to give for a given state and action the value of the objective function. So what I need an index for the capital stock today. So let me call this k index. I need an index for the action to take, which is the capital stock next period. So this is capital stock in the next period, and the index of this capital stock. Then I need to enter the vector of k, and I need a vector for the value function. Okay, and let me end it here. So my capital stock today is going to be the value of k at k index. My capital stock in the next period, so let me call this k next. It's going to be k at k next index. Okay, and from these two things I can already compute the amount of consumption. Okay, so C is going to be the total amount of output that I have available, or capital that I have available, which is k to the power alpha plus 1 minus delta times k, and then minus what I consume in the next, the capital stock of the next period, so this is k next. Okay, so this is my consumption amount. So if c is strictly below 0, then I know that my optimization problem is not feasible. Okay, so if c strictly below 0, then I'm going to output or return a value of that number that's very negative. So here I can use the minus command. So inf is going to be a very, very big number. So it's part of the software, probably the biggest number that computer can generate to some degree. Okay, so if c is smaller than 0, then I'm going to return very negative value. Else I'm going to have to return the objective function, so which is here, so the utility, which is c to the power 1 minus sigma minus 1 divided by 1 minus sigma. Okay, and then plus beta times v at, well, the capital stock next period, so this is k next index. Okay, and this is going to end it here. Okay, so let's compile this, and it's always good if you write a function to at least try to run the function so you see that it gives some output. So for this we need a vector v, of course. So let me take now for the moment some random vector of size 100. Okay, and then let's try to run this. So I need a k index. Let me pick this, for example, 30. The index next period, we pick this to be 20. And then I have to give it the vector k and the vector v, and it should give me a number, okay, which is here 0.887. Let me try to generate a capital stock that's very much bigger. Well, then it's here, this amount of capital the next period is not feasible because it returns a value of minus infinity. So this seems to work just fine. All right, so next I also need a function that computes the maximum for a given k index over all the possible value of k next index. Okay, so let me name this compute max. So as input it has a k index, it has the vector k, and it has vector v. Okay, so here I'm programming very rudimentary. I just want this program to run. Of course you can add whistles and bells and probably do stuff much more quicker than I'm doing here, or much more efficient. The aim here is just to have a program that's running and giving me the output that I want. So what I need to do is I need an output of this function. It's going to give me a value of the objective function. So let me call this solution. Let me put it at some very low for the moment. And then I need a number that's going to give the index at which I have the optimum. So let me put it at some integer value, which doesn't make any sense at the moment. Okay, and then I have to loop over all possible values of next period capital stock. So there are n of them, and I can put, so I can say for I equal to 1 until 100, but now I have the problem that if I change, for example, here the length of my k vector, I have to also change this number, right? So I can get it actually from this vector here, which will be of length n. So I just put here n equal to the length of k, and then I can run from 1 to n. Then if I change the length of this vector at some point here, this will change automatically. Okay, so let me compute a value, which is going to be objective value for k index. K index period is going to be I. I'm gonna have to give it vector k and the vector v. So if I find a value that's bigger than solution, I'm going to update the solution. I'm going to update the opt index. It's going to be equal to I in this case, right? So I'm going to end these loops, and then I'm going to return solution opt index. Okay, so let me see if this works. So compute max. If I give it, for example, at capital stock 50, right? And then I have to give it vector k and vector v. It should give me a number for the value, okay, and then the index number at which the optimum is reached, which is here 3. Okay, so this looks good for the moment. Then I need a function to compute a new value function. Okay, so the new value function is going to take as inputs k and v. So what I need to do is I have to loop this over all values of k index. Okay, I'm going to store this in a new vector, which is going to be tv. It's going to be a vector, and let me initialize it as a vector of zeros of size n, and here again n is going to be the length of this vector k. And I'm also going to store the solution, which I'm going to store in the vector gamma. It's going to be a vector of zeros, and now it's gamma is only going to contain integers, right? So I'm going to specify that this is a vector of integers. Otherwise, my computer will give me an error, I know in advance. Okay, so now I'm going to loop for I equal to 1 until n. I'm going to compute tvi, and gamma I is going to be equal to compute max of k index at I, and then k, and then v. No, not compiling. I'm going to end this. Yeah, I know there's an error. I'm going to return tv, and I'm going to return gamma. Right, I'm going to end it, and now it should compile. So if I compute new value function of k and v, now this gives me a vector of all the new value function, right, which is this one, and then a vector that says at which index I'm reaching the maximum value. Okay, so to finish up, I need one more function, and this function is going to iterate this function over and over again. Okay, so function, let me call this value function iteration, and it's going simply to take the vector of capital stocks. Okay, so I need a vector. First I need the dimension, which is simply this. Then I need a vector. Let me just start with the vector of zeros of size n. I need another vector for the next iteration, and I need a vector of solutions. And this is going to be zeros of integer values of size n. Okay, and then I need each time at each iteration I'm going to compare the distance between this v and this tv, right? And if this distance is below some threshold, then I'm going to stop the iteration. Okay, so I will need to have some variable that captures the distance, and let me put it at some arbitrary big number now, let's say 10, and then need a cutoff for when this distance is below some threshold. So let me call this epsilon. I'm going to put it at some small number like 1 to the minus 6. Okay, so that's normally 6 zeros with a 1. And then I'm gonna have a while loop. Okay, so while the distance is still bigger than epsilon, I'm going to iterate this, right? So I'm going to compute tv, and gamma is going to be equal to new value function at k and v. Okay, then I'm going to compute the distance is going to be equal to the maximum of the absolute value between v and tv, and here v and tv are vectors, and the absolute, so in Julia, if you want to use a function that you want to apply to a multidimensional vector, normally you put a point after the function, right? So there's that use the absolute value function but apply it to the input, which is going to be a vector. Right. Okay, so this should give me the distance, or the maximum distance between v and tv. Okay, so once I have this, it's going to check if the distance is bigger than epsilon, and then it's going to iterate, but now I have to use the output TV of the previous period in return for the function v instead of the function v here. Right, so I have to switch v with TV here. And here this is something particular about Julia and also Python. If you write an assignment like this, Julia is not going to copy the contents of TV and put it into v. No, it's going to assign the name v also to the vector TV. Okay, so when in the next iteration you're going to change TV, then actually you're also going to change v at the same time. And this is something that we don't want, right? Actually we want to copy all the values of TV into v. So you have to put the command copy here, right? So copy here says that take all the values of TV, put it in the vector v, which is going to be then inputted in the next iteration here to compute a new value of TV. Okay, so we're going to end this, and then maybe end this, and then we're going to return once the distance is smaller than epsilon. Is going to skip this loop, and we're going to return TV and comma. Okay, or we can actually also return v, right? Because v is going to be equal to TV. So here we're going to end, and maybe it's easy also to provide some output to this algorithm. So let's first count the number of loops, right? So here we set it at 0, and then at every iteration we can add 1 to the number of loops, right? So you can do this. Plus equal actually says that take the variable loops and add 1 to it. Okay. So let's put loop number loops, and then with the distance. So we also have an idea of the distance, how far we are from obtaining the threshold epsilon here. Right. So this should output where we are at the algorithm. Okay, so let's compile it, and let's now try this. So I'm going to store this at my optimal value function, and then optimal policy function, value function, iteration, and I only should enter the capital stop K. So fingers crossed, let's see what happens. Okay, so you see here at the bottom I'm looping 200 times, right? So after 200 times the distance has reached something that's smaller than my epsilon, and you see indeed that, so number 1, I start with a distance of 1.3, and at every iteration it goes down, right? So this is this contraction mapping property, that the distance between iterative value functions actually gets smaller and smaller and smaller until you converge to below your thresholds. Okay. So what we can do is so this shows that it converged. So let's not plot with a small p. So let's make some graphs here, right? So this is a big package, so it takes some time to load into memory. But what we can do is we can plot k on the x-axis against the optimal value function vs on the y-axis. Okay. Then we can maybe also plot k against the k in the next period, right? So if k is, so let me try to plot it here. So it should appear here next to it, the pane plots. So let's wait a minute. The first plot is always taking a bit more. So what we can also do is we can plot k today against k tomorrow, and k tomorrow is going to be k of gamma it doesn't want to, it's too busy taking the picture, so let's wait a little bit. Okay, yeah, that's the one. So gamma ast is a vector that points you to the capital stock and the index of the capital stock next period, right? So if I input it into the vector k, this vector will now contain the values of the capital stock in the next period. Okay, so here on the right hand side we see it has compiled the first one. So you have k on the x-axis and you have the value function on the y-axis. So you see that this gives you a nice concave function, and for each capital stock k, it gives you the value v of k, right, which is the function, the fixed point that we computed. Okay, so let's plot the second one. So here we see that this gives you somehow of a straight line. So it's a bit wrecked here because I only used 100 values. So maybe I can increase this to 1000. Let's see what it does now. So we can run the same functions. It probably will go a little bit slower. Oh yeah, it goes much slower. So let's cancel this. I don't have too much time. So maybe I can make this 500, which is already 5 times bigger than my first one. Okay, so you see again that here the distance goes down, right? And it should reach a value of 1 to the minus sixth. Right? So I'm at a -3, I think. Of course, the lower you take epsilon, the longer this will take to converge, right? But you see that if these numbers go up in your algorithm, then you know you have done something wrong in terms of programming, right? You have made an error. So I'm already at 4 digits, 5 digits. So if this goes below 1, then the algorithm should stop, I think. Come on. Almost. Right. So, alright, finally. So let's now plot this again, right? So here you have the value function as before. Plotting capital against capital stock tomorrow. Now you see you have the smooth line, okay? So what we can also do is we can plot k against k, and let's put it in the same plot, right? So here is the red line, is the 45-degree line, and here we have the blue line, which gives you for every capital stock the capital stock tomorrow. And here we see that in the end we're going to converge to this point, to the intersection of the two, right, which is going to be the capital stock in the limit. Okay, so basically this is the capital stock today, and this is the capital stock tomorrow. And let me put here the 45-degree line. Okay, so here I have 45-degree line, which means that the capital stock tomorrow I can easily project it until the capital stock today to iterate this process over again. Okay, and then I had another graph which basically gave me gamma of kt, right, which gives you the optimal capital stock tomorrow in terms of the capital stock today. So let's assume that here I start with the capital stock of 0, then I have to look at this function in order to obtain the capital stock tomorrow, which is my k1. Okay, and then I can use the 45-degree line to project this back to the capital stock today, and then can use this one here, this gamma, in order to get the capital stock in 2 days. I can project it back to today using the 45-degree line, and so on. Okay, this is k3 and so on, right? So basically what I will have is I have this kind of a zigzag pattern, and in the end this will come closer and closer to this point here, which you can say this will be my capital stock in the long run, right? I will converge to this point. So what happens if I start at the capital stock here today? Well, I can do the same exercise. This will be the capital stock tomorrow. Then I go with the 45-degree line and so on. So I have here a zigzag pattern in the reverse direction. Okay, so it also goes to this level of capital stock in the limit. Right, so using this kind of figure, you can look at the dynamics of the model and you can see whether it converges to stable equilibrium or not, right? So if, for example, if it would have happened that this would have been my gamma k, right, then starting at some point here, I would have decreased my capital stock in the limits. If I started at some point here, I would have moved further and further away from the capital stock. So right, so this would have been a point of instability, right? So small deviation from this point onwards would either move you down or up, right? So this is what we call an unstable equilibrium. This is a stable equilibrium, right? So in this kind of model, we have just generated this figure. Actually, we have a stable equilibrium. And then this also shows that we can start from some capital stock and you can actually simulate the path towards equilibrium. Okay, I'm not going to do this, but you have all the results from the program and actually to do this kind of dynamical analysis of your model here. So it's just a very simple model, but okay. So one thing that's quite slow in the model is the optimization step, right? So now we basically iterated to every possible action that we could take. And then we only updated the value if we found something bigger, right? Because this is, in general, this is a very bad idea because it's a very lazy way of optimizing a function. So however, we know that the objective function is concave, right? Because of the theoretical analysis beforehand. So basically we can be a bit smarter here. So in the sense that, so if these are all my levels of capital, I have a discrete grid, right? So this is levels of capital. Basically, I want to optimize a concave function, right? Or a concave discrete function in the sense that it first increases, then it reaches some optimal value, and then it decreases later on, right? And if, so this is my choice variable kt plus 1, and if at some point kt plus 1 is too big, then basically I'm going to minus infinity because it's no longer feasible, right? So this is the kind of function that I would like to optimize, right? It first increases and then it decreases. So there's a unique maximum point here. So what I could do in order to there are probably many things that you can do to find the optimum faster than just, so what we did now is we computed this value, right? And we computed this value and said if it's bigger, okay, substituted by this one. And then we computed this one, and then we computed this one, and then this one, and then this one. And then this one, and then this one, and then this one, and then this one, and we got stuck with this one, right? So basically we went over all these values, even these ones, actually, to find the maximum, which is a very bad idea because you don't take advantage of this structure, okay? So one thing that you can do, well, is you can use a lower bound and an upper bound. Okay, so the idea is I know that my optimum is between my lower bound and my upper bound here. And then I can take a point here between the two, let's say this one here, and I can evaluate the function at this point, okay? And then I can take, for example, this point, which is the next one, and evaluate it here. And I can compare this value with this value. And then if the second one is bigger than the first one, I know that I'm moving on the upwards part of my graph. So I know that if there's an optimum, it has to be to the right of this point. So what I can do is I can update my lower bound to this value here. Okay. Similarly, if I, for example, am at this point, right, I can take this point, I can take the next one. So here the next one is lower than the first one, so I know that I'm in my downward path of the graph, so I know I can move my upper bound to this point here, right? So basically I can take a value in between, and each time I can move my lower bound and upper bound closer and closer together until they converge to the point where my graph is maximum. Okay, and this will give me an algorithm that's way more efficient than the current one that I have. Also, if I, for example, sample this point and I get to minus infinity, I can easily move my upper bound here because I know the optimum is going to be somewhere over here. Okay, so let's go back to our coding. So what you want to do is you want to optimize this function here, compute max. I'm already cleared out all the code that you don't need anymore. So here I'm going to have an upper bound. It's going to be equal to n, and then my lower bound is going to be equal to 1. So for Python, counting starts at 0, right? So, but this is Julia, so start counting at 1. For Python, you have to change this to 0. Okay, so we're going to have a while loop. So while the upper bound is different from the lower bound, so I'm going to take the midpoint of these two, and I'm going to put it at the value test. So this is going to be upper bound plus lower bound divided by 2, but I want an index, right? So I'm going to take the floor, which is the biggest number or integer below the mean here, and then I'm going to have to convert it to an integer because I want to use it as an index. Okay, so I get this function here. Then I want to compute the value of my objective function at this index here. So let me call this value is objective value at test, no, at k index of test. Then I'm going to give it k and v, and I want to compute the value at the next index. So let me call this value next is objective value of k index test plus 1 of k and v. Okay, and because here I've taken the floor, I know that test plus 1 always exists. Okay, so that's not a problem here. So if value is equal to minus infinity, right? This means that my objective function evaluates to minus infinity, so the problem is not feasible. I can put my upper bound equal to the value of test. Okay. Also, if it would happen that value is smaller than value next, well, then I know that my optimum is to the right of value next, so I can put my lower bound equal to test plus 1. I can update my my solution, sorry, to value next, and my opt index to test plus 1. Okay, and then else I know that value is bigger than value next, so my maximum value is to the left, so I'm going to update my upper bound to test. My solution is going to be value, and my opt index is going to be equal to test. Okay, and then I'm going to have to close the while loop, and then I'm going to return solution and optimal index. So let's compile this and let's see if this indeed runs faster than our previous algorithm. So here I still have vector of the grid size is still 500. Okay, so let's run this algorithm and see if it runs faster. And you see indeed by the speed of this algorithm that indeed it goes much faster than previous run. Okay, so it should go to 200. And given that it runs faster, we can even increase the size of the grid to, let's say, 1000. Right, so here now we have 1000 points at which we have to compute the function, and even for 1000 points it goes reasonably fast. Right, so you see by making the optimization or the maximization more efficient by using maybe some properties of the value function, right, of the objective function, you can get a huge increase in speed of the algorithm.